So we want to find the dimensions of the largest rectangular box in the first octant with three faces in coordinate planes and one vertex in the plane x plus 2y plus 3z equal to 6. Because a lot of words that feel like they might not have a whole lot of meaning until we discuss them. So let's draw a picture real quick and we'll kind of talk about what all these things mean. So here's the picture of what's going on. We have our usual XYZ coordinate system. And we're looking at the first octant where everything is positive. X is positive, Y is positive, Z is positive. So we're not like back behind the YZ plane. We're not to the, to the left of the XZ plane, and we're not below the XY plane, right? Again, if we're thinking of, I feel like if we're thinking of that corner as the origin, we are sitting in the first octant where X is positive, Y is positive, and Z is positive. And so then we've also got this other plane though, the plane X plus 2Y plus 3Z equals 6. When I draw a plane, if I can, I usually just like to find the intercepts. So if we set X and Y equal to 0, we're going to get a Z-intercept of 2. If we set Y and Z equal to 0, we're going to get an X-intercept of 6. And if we set X and Z equal to 0, we're going to get a Y-intercept of 3. And I said X equal to 6, and I wrote X equal to 0. Let's change that 0 into a 6. Those are my three intercepts. And I could write like Z equals 0, 0, 2, and X is 6, 0, 0, and Y is 0, comma 3, comma 0, but we don't need to. So trying to graph this somewhat decently. 1, 2, 2, 3, 4, 5, 6, and Y is 1, 2, 3. So then we're just going to connect the dots. Somehow I lost my little ruler that I used to have. So here's part of the plane that we have the equation for. It obviously continues like kind of being slanty like this, like all the way, but that's what we got. And now we're going to draw just some box that has the following thing. So it's sitting, what do you say? It's sitting in the first octant with three faces in the coordinate planes, basically just meaning one of its corners is at the origin, one of its faces is on the back wall, one of its faces is on the side wall, one of its faces is on the bottom floor. So let's grab a different color pen here. So maybe it looks like this. It's kind of like going out this way and down this way, maybe over this way and down this way, and then over like here. And like right there is where it's touching the plane. So maybe that's my box right there. Hopefully, yes, let me draw that a little bit darker so hopefully you can see that decently. So like that back plane, oops, sorry. The back part there is touching the XY plane, the left part there is touching the YXZ plane, and the bottom part here, right, that's touching the XY plane. Okay, all said, we're going to say, well, this point here, we don't know its coordinate, but we're going to say its coordinate is X, comma, Y, comma, Z. Or whatever letters you like, A, B, C, D, E, F, and X, Y, Z is typical. What we mean by that is we're saying that this dimension is X, this dimension is Y, and this dimension is Z. So the volume of the box, I know we didn't say we're trying to maximize volume, but the problem said find the dimensions of the largest rectangular box. And when we say the largest thing, it's usually the largest quantity of like the biggest dimension it occupies, right? So since this box lives in three-dimensional space, we want to maximize its three-dimensional volume, not its two-dimensional area or one-dimensional length. So we're trying to maximize the volume. And not too terribly, the volume equation is X times Y times Z. And as we saw last week, pretty typically, the thing we're trying to maximize starts off as a function of one too many variables, right? It's a function of x, y, and z, and we only know how to maximize functions of two variables. So we need a constraint. And here, our constraining piece of information is that the other corner of the box that's not the origin has to sit on that plane. So our other equation, our constraint, is that x plus 2y plus 3z equals 6. And typically, I would isolate z and then plug it into the other equations and write a function of x and y. But it feels like it'd be so much easier to isolate x. Right? I don't need to introduce fractions. I can use y and z as my variables instead of x and y. So let's do that instead. So let's solve for x and say that x is equal to 6 minus 2y minus 3z. And then we will write our new volume function. Our volume is a function of just y and z because we're going to replace x with that. Is going to be x, which is 6 minus 2y minus 3z, multiplied by y times z. And before we start finding our partial derivatives and setting them equal to 0, I think we should multiply it out first, right? I don't need to use the product rule to find my partial derivatives here. I would much rather just multiply it out and make my life easier. I also like to move this back and make my life easier. These desks look like they have so much room, and all these cords make them feel like they are less roomy. So let's see here. We want to, let's turn on this light too. I mean, it's a little bit better. Great. So let's see. So our volume equation as a function of y and z is looking like 6 times y times z minus 2 times y squared times z minus 3 times y times z squared. Not too shabby. Let's take our partial derivatives. Our partial with respect to y is going to be 6z minus 4yz minus 3z squared. We're going to set that equal to 0. Our vz is going to be 6y minus 2y squared minus 6yz equal to 0. Both of those look pretty gnarly. Here's the thing we need to do. So both of these look pretty similarly complicated, right? Like neither of them look like they're easier than the other one, but in each of them we can factor something out. So in this first one here, we can factor out a z from each piece. So we have z times 6 minus 4y minus 3z. And similarly here, we can factor out a y and get y times 6 minus 2y minus 6z equal to 0. So I'm going to be more general than I really need to be here for just a second because I want to point out how you would solve this very generally. If I was trying to find all the critical points, well, I want this equation to equal 0 and this equation to equal 0 at the same time. What means is I'm going to have either this factor equal to 0 or this factor equal to 0. And either this factor equal to 0 or this factor equal to 0. So there's going to be 4 different ways of combining those to get the whole thing equal to 0. Either that's 0 and that's 0, or that's 0 and that's 0, or that's 0 and that's 0, or that's 0 and that's 0. So we're not going to solve all these, and I'm going to show you why. So to find our critical points, we're going to say, well, we could either have z equal to 0 and y equal to 0. That's the first one. The second one we would find by doing z equal to 0 and the other factor equal to 0. 6 minus 2y minus 6z equal to 0. I'm going to solve it. Who can I kid? This one's easy to solve though, right? If you set z equal to 0, you're going to be left with 6 minus 2y equal to 0, and y is going to have to equal 3. Now, the third equation is going to be y equal to 0, and 6 minus 4y minus 3z equal to 0. And setting y equal to 0, we're left with, set 6, not 6y, 6 minus 4y minus 3 is equal to 0. Setting y equal to 0, we get 6 minus 3z equal to 0, which means z is going to have to equal 2. And let me tell you, so far, None of these are the one that's going to maximize the volume of our box. Because if any of your dimensions is zero, your volume is zero. So we could have thought about this a little bit more carefully and just ignored those. But I wanted to point out that if this was a more like, if this was not an optimization problem, but you were just given this function and asked you to find the critical points, you would want to find all four critical points, both y is 0 and z is 0, y is 3 and z is 0, and y is 0 and z is 2. But then the one that's actually going to matter is where you set this equal to 0 and this equal to 0. So we're going to set 6 minus 4y minus 3z equal to 0 and 6 minus 2y minus 6z equal to 0. That looks worrying. No, it's not. I'm making myself worry for a reason. For a moment, I thought those lines were parallel, which was going to be a problem. They're not parallel. I was interchanging two values. Okay. If I was trying to solve this equation, I'd probably multiply this second, or I should say, if I was trying to solve this system of equations, I would multiply the second equation by -2 and get -12 plus 4y plus 12z equal to 0. And then I take this other equation, 6 minus 4y minus 3z equal to 0, and add them together. -12 plus 6 is going to be -6. 4 plus -4 is going to give me 0y, which is why I multiplied it by -2 in the first place. And 12 plus -3 is going to give me 9z. So we're going to get 9z equal to positive 6. Z equal to 6 divided by 9, which reduces to 2 divided by 3. And then if we plug back in for y, into either one of these equations to solve for y, let's plug it in here and say we're going to have 6 minus 4y minus 3 times 2/3 equal to 0. So then we're going to get 6 minus 3 times 2/3 is minus 2. That's going to equal positive 4y. So we're going to get y equal to 1. So our other critical point is going to be y is 1 and z is, where'd it go? 2/3. Even though it's pretty much a guarantee that the only point you found that actually makes any sense is going to be the thing that maximizes the volume or minimizes the thing if you're at, right. Usually the one point you find that makes sense is the thing that does the thing you're trying to find to do the thing you're asked to find. You should still check. So let's do the checking real quick here. So let's see. There's our Vy and our Vz. We're going to find that, yeah, I probably need more room here. Let's see. Vyy is going to equal 0 minus 4z minus 0. Vzz is going to equal 0 minus 0 minus 6y. And finally, Vyz, the mixed partial, is going to be 6 minus 4y. Let me double check this. 6, I thought it was going to be less complicated. 6 minus 4y minus 6z. Let's check the other equations mixed partial just to make sure. If we do Vzy, we're going to get 6 minus 4y minus 6z. Yeah, it checks out. Okay, cool. And then using all the paper, we're going to say, great, our capital D is going to equal Vyy times Vzz minus the mixed partial, 6 minus 4y minus 6z squared. And then we're going to check all of our points. So we're going to look at, even though we know they're not all, still worthwhile. So we plug in 0, 0, we get 0 minus 6 minus 0 minus 0 is 6 squared. That's definitely negative, so we know that's a saddle, not a maximum. If we plug in, what else have we got here? 3 for y, 0 for z. I'm definitely thinking that's a 6y, sorry, apologies, that's a y there. So 3 for y, 0 for z. So it's going to be 0 times it doesn't matter, minus 3 for y, 0 for z is going to be 6 minus 12 squared. Still going to be negative. Still getting a saddle. We probably get a saddle for the other one as well. At 0, 2, it's going to be a 0 there, minus, it's got to be negative, unless that's 0, which is not. You're going to have 6 minus, Yep, 6 minus 12 again. It's kind of interesting how they all turn out to be exactly negative 36. It's probably not actually meaningful, but it's just kind of noticeable that that's negative 36 and that's negative 36 and that's negative 36. So interesting. Finally, the one we actually care about and could have only really done, if we look at d of 1 comma 2/3, we're going to get, let's see, so negative 4 times 2/3, negative 6 times 1, minus 6 minus 4 times 1, minus 6 times 2/3. And 6 times 2/3 is 4 squared. So let's see, if we calculate this, it's going to be negative 8/3 times negative 6, which is, let's be smarter about this, James. Negative 6 times negative 2/3 is negative 4, and negative 4 times negative 4 is 16. Minus 6 minus 8 is negative 2 squared. We're in good shape. That's going to be positive. We still need to check, though, our second partial is negative, and they are. There's your fx, or sorry, your vyy, and there's your vzz. Both of them are negative. So certainly vyy is negative, which means we are concave down, which means we have a maximum. And we're not quite done. Because you go back and read the original question said, find the dimensions of the largest rectangular box. We found y and z, we haven't found x yet. So you have to go back and look at our equation. Oh yeah, our equation was, well, when we solved for x, it was x equal to 6 minus 2y minus 3z. So if we plug in y equal to 1 and z equal to 2/3, we're going to get x being 6 minus 2 times 1 minus 3 times 2/3, which is 6 minus 2, which is also 2. So x is equal to 2. Y is equal to 1, and z is equal to 2/3. So those are the dimensions of this particular box that maximize its volume. Yeah, neat. Something kind of interesting I think is just worth noticing is, and this kind of happens in a similar way with two-dimensional things, is all of those are exactly a third of the way from the origin to like the intersect point. Right? The x-intercept is 6 and x is 2. The y-intercept is 3 and y is 1. And the z-intercept is 2 and the z value is 2/3. That's probably also not a coincidence. Like if you had some other plane that was cutting the XYZ axes in the same sort of way, and you're looking for a box in the first octant, it would probably be exactly that X was a third of the X-intercept, Y was a third of the Y-intercept, and Z was a third of the Z-intercept. Yeah. Probably just because it's, I mean, we could certainly write a question that wasn't by just make like we could, but the thing is, no other octant has a name. So if I was going to say like find the dimensions of the box that maximize the volume, where the box has one corner in some other plane and the faces are in the x-axis, the three faces. If that other plane wasn't living in the first octant, you would just kind of, or at least it wasn't cutting it in that way, you would still just find your intercept. So basically, if your intercepts are all positive, your box is in the first octant. But if any of your intercepts are negative and you're kind of asking for the box that's stuck between the origin and the plane, then you're not going to end up in the first octant. All right. Good times. So let's see, things in order here. Optimization. Yeah, let's do one more optimization problem, and then we'll talk about the other thing. Okay, here's another kind of typical optimization type. Oh, I should. There's really two more I should do. One of them is kind of a classic. We'll do this one for sure. Oh, I know what the other thing was. All right. So actually, two things I should say. If your instructor talks about double integrals, let me know. Although I'll be on the lookout for it. If your instructor talks about Lagrange multipliers, let me know. Not something that always gets covered in this class, but some people do cover it. And it's another way of optimizing stuff. So I don't expect that to come up, but I could be wrong. So please let me know if your instructor talks about Lagrange multipliers. All right, well, let's look at probably two more examples. So find the shortest distance from the point 2 comma 1 comma negative 1 and the plane x plus y minus z equal to 1. And not that we need to graph it, but I do think it's just kind of nice to graph it to kind of have an idea of what's happening. So I'm going to draw the plane. Again, really, I'm going to draw this plane by just finding the x, y, and z intercept. It's not so easy if your intercept is like the origin, then drawing the plane is like terrible because it's just weird to get the perspective right. Unless you're a better drawing than me, which you totally might be. So you might be much better drawing these planes than I am. Great, I hope you are. So here's my x, here's my y, here's my z. And let's see, looking at my equation here, my x-intercept should be positive 1, my y-intercept should be positive 1, and my z-intercept should be negative 1. So I've got something that's like kind of like here, then here, and then here. So my plane, let's use purple, I like the color purple. So here's my plane. So the part of it we're seeing is sitting below the xy plane. And you know, remind you, right? That's just a small portion of this infinite plane that goes in, the different directions. And then the point 2, 1, negative 1, let's see. If that's 1, and that's 1, and that's negative 1. 2, 1, negative 1. Probably sits somewhere like, we'll draw like over here. So we're trying to find some point on this plane that's closest to this point over here. That's not really what the question asked, though. I feel like my drawing is not great there. That's not very straight looking. Okay. Here's the point 2, comma 1, comma negative 1. They didn't really ask us to find the point on the plane. But if you're trying to find the shortest distance between a point and a plane, you're trying to identify where on that plane is closest to this point that's not on the plane. Or in other words, you're trying to minimize the distance between this point that we know and some point that happens to live on this plane. So really, we want to minimize the distance between this point over here, which we're going to call, not surprisingly, x comma y comma z, and the other point that we know, 2 comma 1 comma negative 1. If we knew this point, there would be nothing to do, right? We'd already know the 2 points, and we would just say, oh, the distance is what it is. So that's going to look like minimizing the distance, which is, I should use a lowercase d here because capital D means something else in our class. The distance, which is the square root of the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. Fun fact, useful fact. Instead of minimizing the distance, you can minimize the square of the distance. Let me say this another way. Instead of trying to make the square root of all this stuff as small as possible, you can achieve the same result by making sure that the insides are as small as possible. If the inside of the square root is as small as possible, the resulting square root will also be the smallest possible thing you could have gotten. So that's which is it's always true. So in other words, instead, we can minimize the distance squared, which is just x minus 2 squared plus y minus 1 squared plus z plus 1 squared. In case that feels a little bit hand-wavy to you, let me go real quickly to another piece of paper just to show you why. Let me just point out, if someone said, I'm going to do this as a function of one variable to make it a little bit easier to say. Let's say someone said they wanted you to minimize something like f of x equal to the square root of x minus 1 squared plus 2x minus 3 squared. Pretending like that's my distance equation for a second. Okay. My claim is that you can do it by minimizing just the inside, where you would take the derivative, set it equal to 0, and so on and so on. Let's do it this way, though, just so I can point out what I'm trying to say. If I take the derivative of this, my f prime of x, well, I've got a whole bunch of stuff, x minus 1 squared plus 2x minus 3 squared to the 1/2 power. And my derivative, you do not need to write this down, by the way. I mean, you can, but you don't need to write this down because it's really not that important, except I'm making a point. The derivative of this stuff to the 1/2 power is 1/2 times all that stuff to the negative 1/2 power, which means it's going to end up in the denominator. but it doesn't really matter because it's a distance between 2 points, which shouldn't be zero. So we're not doing zero. And then look what we're going to multiply by. The derivative of the inside stuff. The 2 times x minus 1 plus 2 times 2x minus 3 times the derivative of the inside, which is 2. And if you set that whole thing equal to 0 to find the critical point, you're really just setting this part equal to 0, which is exactly the same as if you had said, I'm going to just look at f of x squared to begin with, which is x minus 1 squared plus 2x minus 3 squared. If you take the derivative of that, the derivative of f of x squared is exactly 2 times x minus 1 plus 2 times 2x minus 3 times another 2. Oh, look, it's the same stuff. So when you take the derivative of the original function and set it equal to 0, or the derivative of just the inside part and set it equal to 0, you're still getting the same thing equal to 0. It's just more work to do it this way. So hopefully that makes it really, really super clear that, oh yeah, it's totally valid to do this. Instead of saying, I'm going to do the hard thing and take the derivative of this square root, well, the partial derivatives, set them both equal to 0, et cetera, et cetera. You can make your life much easier and do it without the square root. Still have a problem though. I got 3 variables there. I only want 2. So I'm going to use the constraint, the fact that your point has to live on that plane, meaning that equation has to be true as far as our point's concerned. And this time I will solve for z. So I'm going to say that z is equal to x plus y minus 1. And we're going to plug that in for z over here. So we're going to get that our distance squared is equal to x minus 2 squared plus y minus 1 squared plus x plus y minus 1 plus 1, or just x plus y minus 1 plus 1 squared. I do not recommend multiplying it out. I don't think that's really beneficial. So now we're going to find our mixed partials. And here I wish I would have called this a different name. Oh well. So you're going to have your d squared x is kind of terrible notationally, but it's what we've got. So our partial with respect to x is going to be 2 times x minus 2 plus 2 times x plus y equal to 0. And I keep saying mixed partial for some reason. Our partial with respect to y is going to be, again, we're not squaring it. It's just our function is called d squared. It's going to be 2 times y minus 1 plus 2 times x plus y. And now hopefully we can do something that's going to make sense here. So simplifying this, I have 2x minus 4 plus 2x plus 2y equal to 0. Isolating y, dividing both sides by 2 and isolating y, I'm going to get y equal to, let's see, that's going to be 2x plus 2x is 4x, divided by 2 is 2x, subtracted to the other side is negative 2x, negative 4 divided by 2 is negative 2, added to the other side is positive 2. So that equation is y equal to negative 2x plus 2. And then this other one is going to be 2y minus 2 plus 2x plus 2y equal to 0. Again, solving for y, I've got 4y equal to negative 2x plus 2. So y is equal to negative 1/2 x plus 1/2. And then we can set these equal to each other. That's probably not the best way to do it. Sorry, my brain just kind of went to the place where I solve for y both ways and then set them equal to each other. But it probably would have been easier to like do elimination or something. Oh well, we're at where we're at. So we solve for y for both of them. Now we set those equal to each other. So we're going to set negative 2x plus 2 equal to negative 1/2 x plus 1/2. I'm going to multiply both sides by 2, undoing the dividing by 2. Oh well. Negative 4x plus 4 equals negative x plus 1. So then adding 4x, subtracting 1, we're going to get x equal to 1. And then if we plug that back into one of our y equations, y is going to equal negative 2 times 1 plus 2, which is going to be y equal to 0. Let's make sure it's a minimum. Although really, if you think about it, it kind of has to be. Because you couldn't really maximize this, right? You couldn't get a maximum distance, because if you think about picking a point on this infinite plane, you could always pick a point that's further and further and further away from the point you're looking at. So it definitely couldn't be a maximum. I guess it could be some weird saddle thing, but it's not. So let's make sure it's a minimum. So make sure it's a minimum. So, all right, our d squared xx, looking at our dx here is going to be, let's look at this. That's easier to take the derivative with respect to x again. The derivative of 2x is 2 plus another 2. So a dxx or d squared xx is 4. I think our d squared yy is also 4 because the derivative of this with respect to y is 2 plus 2. And our d squared xy is going to be, let's see, 0, 0, 2. So then there's nowhere to plug in our point. It's just going to be what it is. Our capital D is going to be 4 times 4 minus 2 squared, which is certainly positive. And since our second partials are also positive, we are concave up, which means we have a minimum at x equal to 1, y equal to 0. And then we go back and we find the z coordinate, recalling that z is equal to x plus y minus 1. So we're going to get z equal to 1 plus 0 minus 1, which is going to be 0. So the point 1, 0, 0 is the closest point to the other point, 2, 1, negative 1. Closest point on the plane. And I've done something kind of wrong here. I answered the wrong question. The question wasn't find the point that's closest. The question was, well, so let's double check. The question was find the shortest distance from the plane to the plane, not find the point that's closest. So even though that is the closest point, what they actually do is go back and find the distance. So the distance between these 2 points is going to equal the square root of, well, now I have the points, 2 minus 1 squared plus 1 minus 0 squared plus negative 1 minus 0 squared equal to the square root of 1 plus 1 plus 1, which is the square root of 3. So it is a good reminder that you actually need to make sure you read. Like, it seemed totally reasonable to answer the question the way I was answering it, but it was not the right answer. Still probably would have been worth some amount of partial credit on an exam, but make sure you're answering the question that's actually, with optimization especially, it's very easy to mistake what they're asking for, whether they're asking for the dimensions of the box or the maximum volume of that box, whether they're asking for the point that's closest or the actual distance that is shortest between those 2 points. All right, let's do the other thing. Let's see what my other examples are. So there are a couple homework. So yeah, there's a couple homework problems, at least one homework problem where we have to maximize or minimize some function with some sort of constraint. That looks very, let me refocus that there. It looks very blurry. And in general, if it ever looks kind of blurry, let me know. There's a little focusy button here I can refocus things with. Um, how do I want to say this? I always feel like I'm bad at describing this. So let's say, here's the idea. So this is absolute, not relative or local, but absolute, also called global, maximums and minimums on a closed boundary. Closed boundary / closed region. So let's look at this example. We have the function f of xy equal to x squared plus y squared plus x squared times y plus 4. And we're looking on the region where there's a lot of ways to say this. I'm going to say our domain D is the set of all points x comma y such that the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1. Essentially, it's all the points inside a 2 by 2 square. So graphically, what we have is this in 2 dimensions in our xy plane. We are limiting ourselves to as far right as up or down 1. So the farthest upper right corner is 1 comma 1, and then lower right corner is 1 comma negative 1, and then lower left corner is negative 1, and upper left corner is negative 1, positive 1. It doesn't have to be, but most of the time, the regions you are dealing with are usually rectangles. So the idea is we want to find all the possible x and y coordinates inside or on this square that are critical points of this function. And the next part, when I'm talking about, I'm not going to draw it because I'm just bad at drawing it. So here's the idea. There's three potential types of candidates for critical points. One of them is your usual type, where it's just you're setting both partial derivatives equal to 0, and you're getting some point where the derivative in the x direction is 0 and the derivative in the y direction is 0. So essentially, your tangent plane is just flat. And that looks like that kind of picture right there. It's kind of like a house with a roof that's kind of normalish looking, right? There's lots of different kinds of roofs, but right, your roof has a peak in the middle, and the plane that's tangent to that peak in the middle is parallel to the ground, right? Parallel to the xy plane. Your partial derivative in the x direction is 0, your partial derivative in the y direction is 0. Said another way, the gradient of your function at that point is 0. If your gradient is 0, that means all of your directional derivatives have to be 0. If your gradient is 0, the 0 vector, dotting it with any other vector is going to give you 0 plus 0, which is 0. But your house might not look like it has that kind of roof. Your house might look like it has that kind of roof. Where over here, at that maximum, that pointy corner up there, the derivatives are not 0 in any direction, really. In fact, the derivatives might not even exist depending on how we're thinking about it. But certainly, any corner, whether it's that corner or that corner or that corner or that corner, is a potential candidate for being a maximum or minimum. So we have to check all of the four corners, or there might be three corners of the triangle, but basically, whatever your region looks like, you have to check all of those corners because they could be potential places where you have an absolute maximum or an absolute minimum function value. And then thirdly, which is the one I think is the hardest one, is you could have something like this, where not at a corner, but somewhere midway between the corner points on one of the walls, you have something like that where you have a maximum. Or it could be a minimum if you open like that. So regular critical points we have to look for, corners we have to test, and also we have to look for critical points on the boundaries. So if you think about this one, right, if you drew, let me see, I can't recall that. If you were to draw like, right, a tangent line in that direction there, it would have a slope of 0. So it's a maximum in that direction, and the other direction it's not really changing. So that's not, we're only considering it one way because we're saying we're on this line where one of the variables is constant. We will look in this example, we'll kind of see. All right, so let's go back to, yeah. Here we go. So here's how we approach this. First step, find the regular critical points. So take your partial derivatives. Fx is going to be 2x plus 2x times y, set it equal to 0. Fy is going to be 2y plus x squared, set that equal to 0. I'm probably going to use the first equation because it has less complicated things, right? There's no powers of 2 here. I'm going to factor out a 2x. So I have 2x times 1 plus y equal to 0. So I'm either getting x equal to 0 or y equal to negative 1. I will stress again, when you have a situation like this and you get an x and a y value from one of your partial derivatives, that does not mean that the point 0 comma negative 1 is a critical point. If you plug 0 and negative 1 into the other equation, you get negative 2 plus 0, which does not equal 0. Just want to remind you, right? What we're saying here is, okay, great, x equals 0, and then you're going to plug that in over here and see what y has to be. So if I plug this in here, I'm going to get 2y plus 0 squared equal to 0, which is going to give me y equal to 0 as well. So one of my actual critical points is 0 comma 0. And then I'm going to do the same thing with y equal to -1. If I plug that in, I'm going to have 2 times -1 plus x squared equal to 0. So I'm going to get x squared equal to +2. I'm going to get x equal to plus or minus the square root of 2. And if I wasn't being careful, I would say that the square root of 2 comma -1 and the square root of 2 comma +1 were critical points. And technically they are for this function, but those critical points are not in this domain. The square root of 2 is a number that is bigger than 1. You'd be looking at points that were like essentially like where I've already drawn things. You'd be looking at points that were like kind of like right here and right here, outside of the region. So those are no good. So that's another thing that's important to say. When you're finding the critical points, they have to live inside the region or on the boundary. If they're outside of it, they're out. So far we've got one critical point to consider at 0, 0. Second, all the corners. They're just automatically included. Kind of like in 17a, when you were finding global maximum minima on an interval, you would always test the endpoints to see if you had a max or a min at the endpoints. Same kind of idea here. These are like your endpoints. I don't need to write them down, but I will. 1, 1, 1, -1, -1, -1, and finally, whichever one's left, -1, 1. And thirdly, the hard part. The boundaries, or sometimes we call them the walls because we're thinking of them as like the walls of your house where you could have a maximum or a minimum. Boundaries slash walls. So for the boundaries slash walls, you actually have to find the equation of each boundary. Now, when they're vertical and horizontal lines like this, they're real easy. The equation of this top boundary is y equal to 1. And the bottom boundary is y equal to -1. And the right boundary is x equal to 1. And the left boundary is x equal to -1. So if it's a rectangle, we're in pretty good shape. If it's a triangle, there's usually going to be at least one side where it's going to be like slanty, and you actually have to find the equation of that line. We're not going to worry about that here yet. So now we're going to take our, let's start with x equal to 1. So for the x equal to 1 boundary, we're going to plug that back into the equation, right? Because if we're living on the boundary where x equals 1, then x should be equal to 1. X isn't changing. So our function is going to be f of 1 comma y, and it's going to be equal to 1 squared plus y squared plus 1 squared times y. And we're going to take the partial derivative with respect to the only variable that would make sense. If x is equal to 1, x isn't changing. If we differentiate with respect to x, we would just get 0. We should definitely be differentiating with respect to y. Because we want to know, great, if we're moving in this direction, where is the derivative maybe equal to 0? So we're going to find fy of 1 comma y and get 0 plus 2y plus 1. Set that equal to 0, and you're going to get y equal to -1/2. So one of our boundary critical points is going to be the point 1 comma -1/2, which is living about right there. You don't have to draw your boundary and your region or your region and like all the points on it, but I find it helpful, but not at all necessary. So we're going to do that 3 more times. We're going to do it for x equal to -1, y equal to -1, y equal to +1. So we do it for x equal to -1, we're probably going to get a similar result. So if x is -1, it might not be the same, but let's check. So if I plug in x equal to -1 into my original function, I'm going to have f of -1 comma y, and that's going to be 1 plus y squared plus y. That's the same as we had over here, so the partial derivative should still end up being the same. It's still going to be 2y plus 1. Set that equal to 0, you're going to get y equal to -1/2. So we also have -1 comma -1/2 as a boundary critical point. So x is -1, y is -1/2, right there. All right, let's do the other two. We're going to set y equal to 1. I keep moving my function away because I want to see other things. But if I set y equal to 1, we're going to have f of x comma 1 equal to x squared plus 1 plus x squared. You know what I did every time, which is not super important, but it is a mistake? I forgot the plus 4 every time. It doesn't make a difference because when you take the derivative of 4, it's going to be 0. But technically, right here, I should have said 1 plus y squared plus y plus 4. Here it should be 1 plus y squared plus y plus 4. X squared plus 1 plus x squared plus 4. Sorry about that. Should make sure it's not, yeah, that's fine. And then our partial derivative is going to be 2x plus 2x, which is 4x. And we set that equal to 0, and we get x equal to 0. So 0 comma 1 is a critical point. And finally, setting y equal to negative 1. Check this out. If y equals negative 1, f of x comma negative 1 is going to equal, my function keeps disappearing because I keep moving my paper. But if I plug in, let's see, I'm going to get x squared plus 1. X squared times y is going to be negative x squared plus 4. And if I simplify this, I get f of x comma negative 1 is equal to 5. The x squareds cancel, and my partial derivative is definitely going to be 0, which means there isn't any solution, right? Or another way to say this is on this on which boundary? On y equal to negative 1, on this boundary here, the function's constant. It's all the same level, meaning all of those points or none of those points would be a maximum or minimum. Meaning really, as long as we test one of the corners, we should figure out what's going on. So if your derivative is 0 along one of those boundaries, you just kind of don't even think about any points on there. There's no way of solving that. Or everything's a solution is the more annoying answer. All right, so now we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 candidates. And we have to test all of them. Just like in 17a, we test them all by plugging them back into the original function and seeing which value is the largest and which value is the smallest. And you might get multiple largests and smallest, right? There could be 3 different points that all give you a z value of 17. So all 3 of those would give you an absolute max, if that was the maximum value. So finally, evaluate all critical points in the original function. Again, let's write it again over here just so I remember what it is. F of x comma y equal to x squared plus y squared plus x squared y plus 4. So let's see. So if I plug in 0, 0, f of 0, 0 is going to equal 0 plus 0 plus 0 plus 4. I think you should show as little work as possible here. Looking at the next one, let's see, that was my regular, my normal critical point. Then we have the corners. F of 1 comma 1 is going to be 1 plus 1 plus 1 plus 4. F of negative 1 comma 1 is going to be 1 plus 1 plus 1 plus 4. But f of 1 negative 1 is going to be 1 plus 1 minus 1 plus 4, because that's going to be a 1 times negative 1 there. That's going to be a 5. And then similarly, f of negative 1 is also going to be 5, because it's going to be 1 plus 1 minus 1 plus 4. And then the ones that are less fun, these ones up here. So we have, let's do this one first. F of 0 comma 1 is going to be 0 plus 1 plus 0 plus 4. That's also 5. And then we have f of negative 1 half. Okay, here we might have to write it out. So let's see, we're going to have 1 plus 1 fourth. And then 1 times negative 1 half is minus 1 half plus 4. So let's see, 4 plus 1 is 5. A fourth minus a half is minus a quarter. So we're getting 5 minus a quarter, or 4.75. Or you could write, what, 19 fourths if you wanted to? Okay. And then f of 1 comma negative 1 half probably gives you the same result. Let's check. Plugging in 1, we get 1 plus 1 fourth. Still minus a half, still plus 4. So yeah, it's the same thing. Okay, so I would say the following. We have absolute maximum value is what? 7. And occurs where? Right. At 1, 1 and at negative 1, 1. Similarly, the absolute minimum value is 4.75 and occurs also at 2 points. 1 comma negative 1 half and negative 1 negative 1 half. You could write it as plus or minus 1 comma negative 1 half, which would include both points, right? Right, it's that one and that one. The x coordinate can be negative 1 or positive 1, but the y coordinate has to be negative 1 half. Oh, did I miss 0, 0? Oh, I did. I totally ignored 0, 0. Boo on me. That's wrong. You have to look for the actual smallest value, not the one you think is the smallest. You should look at all of them. Right. So the absolute minimum value is, of course, something I don't have room to write anymore, but I'm gonna squeeze it anyway because it really feels silly. So the absolute minimum value is not 4.75. It is 4 and occurs at 0, 0. Good call. Thank you so much. Question, yeah. It might have been because I missed it. Oh, no, it's right there. Sorry. It's right where you can't see it. I'm pointing to it. Can't you tell? It's right there. No, it's all right. It's easy to miss. Obviously, I miss stuff all the time. Okay, yeah, we got time. All right, cool. So let's see. I had another example on my mind. Let me just double check. That's the one I really want. Is it? That one's kind of boring. Okay, let's look at one more example, but we're gonna do it kind of quick. And then we'll have one after that, which will be a little bit harder. Okay, let me make sure. I've got papers all over the place. Keep things in order here. So here's an easy example, relatively. Same sort of question. Find the absolute maximum and minimum value of f of x comma y equal to 9 minus x squared minus y squared, our favorite upside down paraboloid, on the interval, on the interval of xy coordinates where x is between negative 2 and 2, and y is also between negative 2 and 2. Again, this could have been written in the other way. We could have written this as the absolute value of x is less than or equal to 2, and this as the absolute value of y is less than or equal to 2. That would also be a perfect fine way of doing it. Usual process. So, step 1, regular critical points, which are super easy to find here. Our fx is just what? Oh, I know what I was going to say. It's negative 2x. Our fy is negative 2y. By the way, I want to point out when you're finding regular critical points, you are literally setting the gradient equal to 0. Remember what the gradient is? The gradient is the partial derivatives fx and fy. Oh yeah, you're just setting the gradient equal to the 0 vector. So really, right, which makes sense because you're trying to find out where essentially your tangent plane is flat. So every directional derivative is equal to 0, which would mean the gradient would have to be 0. All right, but it's easy to solve that, right? In this case, you're just going to get x equal to 0 and y equal to 0. So your one true critical point often is going to be the origin. It's pretty typical. Second part, we have 4 corners again. I'm going to try my best not to draw the region here. So my 4 corners are 2 comma 2, 2 comma negative 2, negative 2 comma 2, and negative 2 comma negative 2. Interesting. Anyway, sorry, I was having a thought over here. And then finally, or thirdly, I should say, the walls. So our walls are x equal to 2, x equal to negative 2, y equal to 2, y equal to negative 2. So if we look at setting x equal to 2, our function is going to be f of 2 comma y, and we're going to get 9 minus 4 minus y squared. And if we take the derivative of that, we're still going to get negative 2y. So our fy is still going to be negative 2y, and we set that equal to 0, we're still going to get y equal to 0. So our critical point is going to be 2 comma 0, not one of the corners. Sometimes you do end up getting, when you look at the walls and you set the partial derivative equal to 0, sometimes you do end up getting like the corner 2 comma 2. That can happen. And the same kind of things can happen for every other wall here. So if we set x equal to negative 2, same result. We're still going to get f of negative 2 comma y equal to 9 minus positive 4 minus y squared. And we're still going to get fy equal to negative 2y. And we're still going to get y equal to 0. So we also get negative 2, 0. And in a similar way, we're also going to get 0 comma 2 and 0 comma negative 2. We're going to see that if we set y equal to 2, then our f of x comma 2. Here, let's be smart. Let's be smart about this for a second, just to save myself one line of work. If we set y equal to either plus or minus 2, our f of plus or minus 2, sorry, that should be f of x comma plus or minus 2, is going to be 9 minus x squared minus plus or minus 2 squared, but that's just 9 minus x squared minus 4. And the partial derivative is going to equal negative 2x, which is going to be giving us x equal to 0. So we get 2 more wall critical points, plus or minus 2. Gosh, I keep wanting to write the y part first. 0 comma, let's just try that again, James. X is 0, y is plus or minus 2. So lots of critical points. If you did draw the boundary here, you'd have all the corners, the center, and all the midpoints on each wall. 2 comma 0, 0 comma 2, negative 2 comma 0, 0 comma negative 2. And then we're going to test them all, which always feels like a pain. So we have f of x comma y equal to 9 minus x squared minus y squared. At least it's pretty easy to test them all. So step 4, test them all. So let's see, f of 0 comma 0. So think about it for a second. You know what this parabola looks like, right? It's this downward opening kind of mountain shape. And we know the peak is at 0, 0, 9. If you plug in 0 for x and 0 for y, you're going to get 9 for z, which is exactly what we get. And then f of, no, I'm not. F of 2 comma 2 is going to be 9 minus 4 minus 4, which is 1. And hopefully it's obvious, maybe. It doesn't matter if it's plus or minus 2 here or plus or minus 2 here, since you're squaring both x and y. So really, f of negative 2 should also be 1. F of positive 2 negative 2 should also be 1. F of negative 2 positive 2 should also be 1. And then the last ones, the midpoints here on these walls, f of 0 comma 2 is going to be 9 minus 0 minus 4. And so is f of 2 comma 0. And so is f of 0 comma negative 2. And so is f of negative 2 comma 0. So absolute maximum is f of 0 comma 0 equal to 9. That's kind of like the way, I feel like this is the best way to write it, because writing it this way answers the question, right? It says what the value is 9, and it also tells you where it occurs. So this is saying, oh yeah, my maximum value is 9, and you get it by plugging in 0 for x and 0 for y. You could write more words. You could say the maximum value is 9, and it occurs at the point 0 comma 0. But I think it's more concise, takes up less writing to do it that way. And then our absolute minimum, well, there's a few of them. Absolute minimums are f of plus or minus 2 comma plus or minus 2 equal to 1, which is 4 different absolute minima. And really the reason I wanted to do this problem is so I could show you the picture on Desmos 3D because it looks kind of neat. So here is this downward opening paraboloid restricted to the square that's the 2 by 2 square. And if you check it out, you can kind of, in fact, let me zoom in a little bit. I don't really care about that. Yeah, fine. It's so persnickety. But if you look here, you can see the absolute minima are all those like those lowest points on the bottom there, just hanging out. The absolute, whoops, oh shoot, I forgot geez, what? That's concerning. It's plugged in. That is, Oh, I think this plug didn't work before. Yeah, let me plug this in real quick. Sorry. So my computer doesn't die. Okay, great. We have, oh, so what I really wanted to point out though was that these points right here are those points on the walls I was talking about where it's a maximum along that wall, even though it's not a maximum for the entire function, right? That purple dot right there, or that green dot right there, right? All those four of them, right? That point, if you look along just the line, like x equals 2 or y equals 2, you're getting a maximum in the middle at like the point x is 0 and y is 2, or x is 2 and y is 0. But it's still not the global maximum, right? Because certainly there's a point on the surface that's much higher over there. So that's kind of what I wanted you to see, because I think it's valid to be like, oh yeah, we really do need to consider those midpoints because they can, well, and just kind of give you a different example of another one that we didn't do, but I want to show you anyway. Fine. Here's a different function, a hyperbola, where the points in the middle actually do end up being your maxima and your minima. So those points along the walls are actually really important to make sure we check because they can be where you get your global max or your global minimum. What time is it? We got so much time. We'll do one more example, then we'll call it a day. So one more example of this, which is kind of the most challenging, is turn this light on. Is when your region isn't a rectangle or a square. So let's look at this example. Amazing how much pen ink I go through. Well, let's see. So find the absolute maximum of the function f of x comma y equal to, sorry, let me, 1 second. I need to alternate. This is the boringest function I've ever seen. It's not going to be fun at all. I have a better example over here somewhere. Where did I put you? You are hiding from me. 1 sec. I know where you're at. Apologies. I have to think for a second. I know I have a better example at my fingertips. I just have to find it. One moment. I think it's right here. Let me check. Sorry about that. I thought I had the right example ready to go, and then my computer died. So it's a lie. I'm blaming it on my computer. I didn't have the right example ready to go. The example I had up was all ready to go, but it was not the right example. All right, here is what I wanted, really. Cool. So the function f of xy is equal to 3 plus x times y minus x minus 2y. And we're on the triangular region. With vertices 0, 0, 0, 5, and 5, 0. And for these ones where your region is not some nice rectangular square, I really do think it is worthwhile to draw it. So let's quickly draw our region. So let's see, I've got the point 0, 0, cool. And I've got the point 5, 0, and 0, 5. And I'll point out we're going to need the equation of each of our boundaries. So let's find them right now. So this bottom boundary here on the x-axis, this boundary is the line y equal to 0. And on the x-axis, this boundary is the line x equal to 0. And this boundary is actually a line whose equation we need to find, but it's not that hard because from 0, 5 to 5, 0, I'm going over 5 and down 5. My slope is -1. My y-intercept is +5. The equation of this line is -x plus 5. Usually, if it's a triangular region especially, the line they're going to give you 9 times out of 10 has a slope of +1 or -1, and usually the y-intercept is not hard to find. So whatever slanty line you have in the triangular region, most often will be pretty nice to find. All right, usual stuff. Find the critical points. So regular critical points, my partial with respect to x is going to be 0 plus y minus 1 equal to 0. My partial with respect to y is going to be x minus 0 minus 2 equal to 0. So we're getting a very clear y equal to 1 and x equal to 2. So my critical point is 2 comma 1. You do want to double check and make sure it's actually inside your region, but it definitely is, because if I go over 2 and up 1, right, the point that would be on the line would be like 2 comma 3 or something. So 2 comma 1, definitely good to go. We have our corners, of course. Feels like even silly to like write the points. They're already there, but the corners, we will remember to check them. 0, 0, 0, 5, and 5, 0. And thirdly, the walls. So let's see what's happening along the bottom wall, y equal to 0. So I plug in 0 for y, my function is going to become f of x comma 0 equal to 3 plus x times 0 minus x minus 0. And taking the partial derivative of that, my fx of x comma 0 is going to be -1. What does that mean? Well, it means along this boundary, the slope of my surface is always -1, meaning we're essentially starting up here and ending over here, and we go straight down the whole way. So there isn't going to be a point in the middle that's a potential maximum or minimum, but definitely the corners could be max or min. But we're already going to test the corners, so we're good. So this means no critical point along that wall because you set that equal to 0 and there's no solution. Similarly, along the wall x equal to 0, same sort of result. F of 0 comma y is going to be 3 plus 0 minus 0 minus 2y. And if you take the partial derivative of that, you're going to end up getting -2, which also doesn't equal 0. But interestingly, along the slanty wall, something different is going to happen. So along our third wall, which is y equal to -x plus 5, you're literally going to replace y with -x plus 5. So our function is going to become f of, instead of x comma y, it's going to be x comma -x plus 5. And so we're going to plug in, we're going to get 3 plus x times y, but y is -x plus 5, minus x minus 2 times y, but y is -x plus 5. I do think we should simplify this before we find the derivative. So we're going to write this as 3 minus x squared plus 5x minus x plus 2x minus 10. And it's probably worth it to simplify this even further. That's going to be -x squared, and 5x minus x plus 2x is going to be plus 6x, and 3 minus 10 is -7. And then if we take the partial derivative, our fx is going to equal -2x plus 6, so that equal to 0, we end up getting x equal to +3. And we plug that back into this equation over here, y is going to be -3 plus 5, which is going to be 2. So our critical point along that wall is the point 3 comma 2. That one always feels a little bit harder to get, but it's not that bad. All right, we've got all the points. The last part is the part where you plug it all into the original equation and see what you got. So let's list all our points here. We have, let's see. So we're going to find f of, I'm just going to write them down first and then go back and figure it out. So we're going to have f of 2 comma 1, f of 0 comma 0, f of 0 comma 5, f of 5 comma 0, and finally f of 3 comma 2. Let's go ahead and go back up here. So then using what our function's equal to, f of 2 comma 1 is going to be 3 plus 2 times 1 minus 2 minus 2 times 1, which is going to be 3 plus 2 minus 2 minus 2, which is 1. 0, 0 is easy. It's going to be 3 plus 0 minus 0 minus 0. 0, 5 is going to be 3 plus 0 times 5 minus 0 minus 2 times 5, which is going to be 3 minus 10, which is negative 7. 5, 0, we're going to get 3 plus 0 minus 5 minus 0, which is going to be negative 2. And lastly, 3 comma 2 is going to be 3 plus 3 times 2 minus 3 minus 2 times 2, which is going to be negative 4. Let's see. There's our minimum. And there's our maximum. Unless I'm missing something. Yeah. Cool. So honestly, doing that's usually enough for people. But if we want to be super extra clear, you have your absolute maximum at, or I should say, is f of 0 comma 0 equal to 3. Your absolute minimum is f of 0 comma 5 equal to negative 7. All right. So next time we will talk about, well, if Lagrange multipliers or double integrals come up in class tomorrow, let me know. We'll talk about that. If they don't, we'll start talking about solving systems of linear differential equations, which is kind of kind of the meat of the class for basically the rest of the course, maybe like, except for the last 2 weeks, the rest of the class is going to be talking about solving systems of 2 linear differential equations. Yeah, that's it. And it's definitely going to rely on your ability to find the determinant, eigenvalues, and eigenvectors of a 2x2 matrix. So now would be a really good time to go back and maybe review some of that material so that you're very competent at finding eigenvalues and eigenvectors of a 2x2 matrix. All right, I'll see you all on Thursday. Oh, thank you so much. You should feel free to say something sooner so it's not a bad rush at the end. Yeah. Maybe let's double check. I might have made a mistake. Let's see. So if I plug in 3 comma 2, I'm getting 3 plus 3 times 2, which is 6, minus 3 minus 2 times 2, which is 4. I think I'm going to get negative 4 because 3 plus 6 is 9. Minus 3 is, you know what? So here's what my brain did. I know what my brain did. My brain somehow said negative 3 plus 6 plus negative 3 is 0, and then just caught the negative 4. Thank you very much. That should be 3 plus 6, which is 9, minus 3, which is still 6, minus 4, which is positive 2. Very different than negative 4.